Okay, it's time to start the next unit, which is called Work, Power, and Energy. Okay, so we're leaving momentum and forces behind, and kinematics, but they'll always come back. One will feed into the other, so don't worry about that. Today we're going to look at work. And I could ask you, what is work? But some of you might not know that yet. Some of you have figured it out more and more as the semester passes. But when we talk about work in physics, it's a bit different than what we talk about in real life. Okay? We consider work when a force is applied to an object and it causes the object to move in the direction of the force. So imagine that I have a box and I'm putting a force on the box going this way. If I can make the box actually move, then I've done work. Okay, so work is when a force is applied to an object. When a force is applied to an object, causing the object to move, to move in the direction of the force. Okay? So there's a few important things in this definition. Obviously, you have to apply a force to the object. You have to apply a force to an object that makes the object move. So I could push on my desk all day, but no work will be done because like the desk, the front lab bench, it's going to take me quite a while to move that object. So in order for work to be done, the object has to be moved. So that's one thing. And it has to move in the direction of the force. Okay? So it might be that there's a book. Or no, I know what I could do. Imagine that I'm standing in the classroom holding a book. I have really long arms and legs. Okay, so this is me holding a book. Okay, if I'm standing here and just holding the book, then the object isn't moving, no work is done. If I now walk around the classroom still holding this book, so I'm walking this way, still no work is done because my force is going up and my delta D is to the side. So although the object is moving, it's not moving in the direction of the force. Okay, so work is only done when you put a force on the object that causes the object to move in the direction of the force. So the amount of work done depends upon the force that you're applying, and it also depends on how far you move it. So the equation, it's actually the first time that we're going to be multiplying vectors together because it's force and displacement, and both of these are vectors. And we're going to multiply them together in a special way. It's called dot multiplying. Now I know you've all seen that dot and you know it means multiplying, but it actually originates from, there's two different ways we can multiply vectors. One is dot multiplying, and the other way is called cross multiplying, and you'll see that in grade 12. By definition, when you dot multiply two vectors together, that is the same as multiplying their magnitudes, their sizes together, and then multiplying by the cosine of the angle between them. This is the equation for work, okay? Where F is the force applied, and of course it's measured in newtons. Delta D is the displacement of the object. And of course, it's measured in meters. Theta is the angle between F and delta D. Okay? And then W is the work done. and it's going to be measured in Newton meters. And a Newton meter, we said the other day in class, was renamed a joule. So work done and as well as energy are both measured in joules. Now, let's go back and think about the theta for a few minutes. If the theta, if I have a book on a surface like I did up top, and I'm pushing the book this way, and the book is moving this way, then the angle between them, theta, is 0. And the cos of 0, check it on your calculator, the cos of 0 is 1. So when F and delta D are in the same direction, you get what we would say is maximum work, because all of your force is actually being used efficiently to move the book. Okay? If theta is 90 degrees, like here where I'm walking in one direction and I'm putting force on a book upwards, theta is 90 degrees, the cos of 90 is 0. And so as a result, no work is done. All right? Now it might also be that the angle, the force and the delta D are moving in opposite directions. For example, let's assume that I have that book that I was holding up, but now I'm going to lower it. So this is my hand here putting an upward force on the book. I'll make my arm a little less long this time. But I'm lowering the book down, so my delta D is this way. So the angle between them is 180. And when theta is equal to 180 degrees, cos of 180 is actually -1. So that means negative work is done. But what the heck is negative work? Negative work is when I don't have to do the work, that the object wants to go there, right? I have to put an upward force on this book so it won't free fall. But as I lower it, the book is losing energy. It's getting closer to the floor. The higher up it is, the more energy it has. So as I lower it, it's losing energy, and that's what negative work means. Negative work means the object is losing energy. It would be similar to if you had a cart rolling across the table. So it's rolling this way, so its delta D will be this way. But you decide you want to slow it down, so you're going to put your force on in the opposite direction. The angle between your delta D and your F would be 180, so the amount of work done would be negative, and it's because you're taking some energy, some of its kinetic energy away. Remember, kinetic energy is energy of motion, and by pushing in the opposite direction, you're actually slowing it down, and so you're taking away some of its energy, and that's what negative work means, losing energy. Okay? Now, energy, spell it right. Now, just for a note, if any of the questions tell you you're lifting a box, when you lift a box, we'll always assume it's at constant speed. So you're applying some force to lift the box, and if you're lifting it at constant speed, it means the force you're applying will be equal to the weight. It'll be equal to Fg, which will be mg. So in a question, if it tells you you're lifting a 5 kilogram box, then just know you must be applying a force of 5 times 9.81. Okay, because they're not really great about that. Now, so remember, if you're applying a force that's not in the direction of motion, no work will be done. Or maybe it'll be at an angle. Maybe it'll be those toboggans that we were pulling. Right? Maybe this will be F, and so it'll have a component going this way, and this will be the delta D. So the angle, so then you do W is equal to F delta D cos theta, and if the theta is like 30 degrees, then you just fill in your F, your delta D, and cos of 30. It would be the same as using the Fx component of your F times delta D, because the Fx component is F cos theta. Okay, so you just stick in the F, the delta D, and whatever the angle is between them. Okay, so I want you to try some of these tonight.